Welcome back. We are on lesson 9.2 for physical science. So physical science, make sure you're physical science. If you're biology, you'll want to go find the biology lesson. So 9.2 for physical science, we're discussing wave properties, and the main idea is wave properties depend on the vibration of the wave source and the material in which the wave travels. So it's kind of like a 2-for-1. So currently we are in your textbook on page 279, and we're learning a little bit more about the parts of the wave. So make sure you put in your new heading, the parts of the wave, and underneath that, a transverse wave has alternating high points, known as the crest, and low points, known as the trough. You need to know these are crests, those are troughs. This is a crest, that's a trough. Now, a longitudinal wave is actually a lot different, okay, because it doesn't have any crests and troughs. It doesn't have this high, low, high, low. It doesn't look like that at all. A longitudinal wave has something with the coiled spring again. This example has this compression in this region where the coils are close together, okay? And then next to compression, where they're really spread apart, or it's less dense, we call this rarefaction. Now, we talked about mechanical waves and that there were two types. And the first type, again, is transverse, and the second type is longitudinal. So for understanding mechanical waves, that there's two types and that they also move in different ways. Not only do you need to know all of that, but you need to be able to say, oh, when I see this, this is a transverse wave, because transverse transfers from top to bottom, from top to bottom, from crest to trough, from crest to trough. And a compressional wave is a longitudinal wave. And you need to know the area that is less dense is rarefaction, and the area that is really dense and pushed together is compression. Next heading. A wavelength is the distance between one point on a wave and the nearest point just like it. So let's take a look at this picture. For transverse waves, the wavelength is the distance from the crest to the next crest, or from the trough to the next trough. And for a wavelength, in longitudinal waves, we measure from the distance between the two neighboring compressions, which is here and here is considered a wavelength, or between the rarefaction and here. And of course, those examples are in your book on page 280 as we learn and read more about wavelength. If you would like to ever enter those things in and label the diagrams in your book, it's your book again. This is yours. Take ownership of it. But you certainly do not need to do it. But if it helps you, by all means do it. So a wavelength, the wavelengths of sound waves that you can hear range from a few centimeters for the highest pitched sounds to 15 meters for the deepest sounds. Next heading, frequency and period. The frequency of a wave is the number of wavelengths that pass a fixed point each second. So two examples of that. You can find the frequency of a transverse wave. Remember, transverse goes up and down, has a crest and a trough. You can find the frequency of a transverse wave by counting the number of crests or troughs that pass by a point each second. And you also need to know that frequency is expressed in hertz, capital H, little z. This is your SI unit for frequency. And speaking of frequency and period, you do have some more vocabulary words. Here's one of them. The period of a wave is the amount of time it takes one wavelength to pass a point. So the bullet point under that needs to be, as the frequency of a wave increases, the period decreases. And periods have units of seconds. So we have shortly discussed wavelength and frequency, but now we need to talk about them together. And currently we're on page 281. So wavelength is related to frequency. So make sure you write all of that down. As frequency increases, wavelength decreases. The frequency of a wave is always equal to the rate of vibration of the source that creates it. So if you move the rope down, up, and back down in 1 second, the frequency of the wave you generate is equal to 1 hertz. So the second thing you need to know about wavelength being related to frequency is this. The speed of a wave depends on the medium it is traveling through. Remember, everything is on a molecular level, okay? Even though we see solids, there's molecular levels to it. And if you go back in your memory about molecular level, what those molecules look like inside of a jar, if it was a solid, they were all tight, squished, packed, very close together, almost like holding hands. Red Rover, send somebody over, right? Super, super close, tight knit. And then we had liquid, and liquid kind of slid past each other, still kind of tight, but it was kind of loosened up and just kind of going with the flow, you know, it's all right. And then you had air or gas, and it was just kind of they were just kind of everywhere. They weren't tightly packed at all. So that brings me to my first bullet point. You'll want to write this down. Sound waves usually travel faster through liquids and solids than they do through gases. However, light waves travel more slowly through liquids and solids than they do through gases or through a vacuum. Before we go to this one, I want to talk about this for just a second. Clearly, because our molecules, the closer they are together, the faster sound waves can move through them. That's why liquids and solids being so tightly knit together here and sliding past each other here for the liquid, that's why it travels. But like many rules, there's always that exception. This is your one exception. So what I'm telling you is you need to know this rule right here. But you also need to know the one exception. Second bullet point, sound waves usually travel faster through warmer materials than through cooler materials. So how do you calculate the wave speed? Well, you can calculate the speed of a wave represented by V by multiplying its frequency times its wavelength. So what I would like you to do is take frequency times wavelength equals speed. Our next heading for lesson 9.2 for physical science, amplitude and energy. Amplitude is related to the amount of disturbance from a wave. What does that mean? These 2 bullet points will tell us the greater the wave's amplitude is, the greater the disturbance that the wave produces. Amplitude is measured differently for longitudinal and transverse waves. The amplitude of a longitudinal wave is related to how tightly the medium is pushed together at the compressions. So that means the denser the medium is at the compressions, the larger the wave's amplitude is, and the more disturbance that wave will create. So currently we are on page 283, and this is a picture of a closer look at how the coils are compressed, and the closer they are compressed, the farther apart are going to be the rarefactions. So the less dense the medium is at the rarefactions, the more energy the wave carries. Amplitude of transverse waves. The amplitude of any transverse wave is the distance from the crest or the trough of the wave to the rest position of the medium. So if this is our rest position, this dotted line here, okay? So it'd be from the crest to here. That would be our amplitude, from here to here, or from here to there. So one more time, from the crest to here, or from the trough back to there. You will want to go to your online textbook and look at Chapter 9, Section 2, and take a look at the video that is included for that section.